Okay, so welcome everyone to today's Symmetry seminars with Giovanni Galati. We'll speak about topological constraints on defect dynamics. Please take it away.
Okay, thank you very much. And I would like to start by thanking all the organizers for this very nice opportunity. And today I will talk about this paper that I've done recently in collaboration with Andrea Antinucci, Christian Coppetti, which are in Oxford, and Giovanni Rizzi, which is in IHES in Paris. And okay, this work is basically about some study of extended defects in quantum field theory, and how to try to put constraints on their dynamics using some topological argument, using some symmetries of the quantum field theory. Okay, let me start with an introduction and the motivation of why we are interested in this subject. Okay, so the study of extended defects in quantum field theory, I think, is crucial for a variety of reasons. For example, if you are interested in more physically relevant things, if we want to model some experimental setup, defects are very useful because they model impurities of materials. For example, they can model localized impurities or boundaries and interfaces. And these things are objects which are naturally present when we are in some real world scenario, because we cannot avoid to have boundaries, for example, of interfaces. If you are more, let's say, high energy people, defects are also important because they are remnants of heavy particles in the low energy effective theory, which describe light modes. For example, in gauge theories, we are very used to say that Wilson lines are, let's say, describes the word line of very heavy electrons or quarks. In some, let's say, low energy theory, that we don't know what is the UV completion. Okay, there is also another way to say that defects are very interesting, and this because, like for local operators, if we study the correlation function of these extended operators, we can take some information about the quantum field theory in general. For example, if you are interested in the problem of confinement, we know that there is a very precise way to define what do we mean by confinement. And in order to understand this concept, we have to look at the behavior of very large Wilson lines or Toft lines. And we say that if the Wilson line approach a perimeter low behavior, we say that the theory is deconfined. While if the Wilson line approach an area low behavior, we say that the theory is confined. Of course, there are also other set of extended operators which are very useful in quantum field theories. For example, the algebra formed by topological extended operators, we know that is the one that generate all the generalized symmetries of the theory, what we now call the Q-form categorical symmetries. And we know very well that this understanding this algebra gives a lot of constraints on the full quantum field theory, for example, on the allowed phases and transition that a theory can have. Okay, so now that we know what are the objects that we would like to study, I want to present at least what is the definition that we can give of these operators, at least when we have an action and some fundamental fields. So in this context, there are at least two ways to define the defects. One way is to prescribe a boundary condition for the bulk fields when they approach the locus of the extended defect. And a prototypical example of these definitions are Toft lines or disorder operators. For example, Toft lines in abelian disk theories are defined by specifying a fixed behavior of the field strength on the spheres which links with the line. So it's somewhat an implicit definition of the defect in terms of the behavior of the fields of the theory. Okay, there is another way to define defects, which is by local modification of the Hamiltonian or the action. And what I mean with the local modification, I mean that I take my action describing the quantum field theory and I just modify it by integrating a Lagrangian, which is locally defined on a submanifold of the spacetime. And this Lagrangian can depend on of course, on the bulk fields, but also on some edge mode, which only lives on the world volume of the defect, and is somewhat related to the degrees of freedom living on this defect. So in analogy with the example of the Toft line I was giving before, in very prototypical example of this kind of definitions are Wilson lines, for example, in quantum electrodynamics, which have a definition in terms of an action. Indeed, we can think as the insertion of Wilson lines as a local modification of the action locally in a line gamma where we integrate the connection. So of course, in abelian gauge theories, we don't need to introduce edge modes, the sky edge modes. The defect is entirely defined by its coupling to the bulk. So it only depends on the bulk fields. But for example, if we want to consider non-abelian Wilson lines, we know that in order to reproduce the path order exponential and the trace that define the lines, we need to introduce some edge modes, just this Z, which live on the line, and then they couple to the bulk through this coupling. Okay, this point of view as a local modification of the action give also very nice consequence in terms of the normalization of these defects. So indeed, for extended defects which are not local, we know that since they should define a new Hamiltonian, what we call a defect Hamiltonian, this Hamiltonian should be well defined. And in order to have a nice behavior, we have to impose that the partition function has a nice interpretation as a trace over the Hilbert space. And this cannot be true for a generic normalization. And this implies that extended operators have a very fixed normalization. And after fixing this normalization, we can only do linear combination with integer coefficients. Okay, so from its Lagrangian description, it's also very evident that extended operators will generically fill energy flow even when the bulk is conformal and does not run. And there is a very nice way to interpret this energy flow just because when we introduce an extended defect, we will introduce a new scale in the problem, which is related to let's say, to the sides of the defect. For example, we can put the defect on a sphere, and then this new scale will be the radius of the sphere. And then we can compare this scale with the scales of the theory, the one set by the relevant couplings of the theory. And then if the size of the defect is very, very small, is the smallest scale in the problem, then we are in the UV, and the definition that I gave to you before, the one in terms of the fundamental fields, is valid. While if we now start to increase the size of the defect, then we go to the IR, and this is more or less the problem that we would like to study. So understand what is the IR behavior of this defect. For example, in the problem of confinement that I was mentioning before, this is exactly what we want to know. We want to know the behavior of the Wilson lines when the loop is very, very large. So as you can imagine, understanding this RG flow is generically very hard. It's much harder with respect to solving an RG flow for a quantum field theory, because we even lose the full Poincare invariance of the theory. We are breaking Lorentz to a subgroup which preserve the locus of the defect. Okay, however, we have some, let's say, theorems which constrains such RG flows. And in particular, if we assume that the bulk is conformal, so if there is no RG flow in the bulk, the RG flow is localized only on the defect, then we can find some monotonically decreasing functions, which here I'm listing for line operators and for surface operators. These are the so-called G and B functions. And one can prove that these G and B functions decrease along the RG flow, and in particular, their values in the UV, which one can easily compute from the Lagrangian, is always bigger with respect to the one that we get in the IR. And also a very nice property of these functions is that they give a very quantitative count of the degrees of freedom living on the defect. So before I was mentioning that these edge modes that one can introduce in order to define the action are somewhat related to the degrees of freedom of the defect, but this is not very precise because edge modes can always be integrated in, integrated out without so much effort. So it's not very it's not a very quantitative way to count degrees of freedom. What is actually count these degrees of freedom are these GMB functions. Okay, so now that I present the problem of let's say studying these defect archiflows, I would like to list now at least what are the possibilities for these IR defects. Here I'm dividing the possibilities in three ways, but of course one can be more specific or less specific depending on the problem. So the first possibility that I define is when the defect flows to a non-trivial defect CFT. And what I mean with non-trivial, I mean that when I take a bulk operator, and I can always do an OP expansion on the locus of the defect, at least when we have conformal invariance. And then non-trivial is when this OP is non-trivial, in the sense that it's not just a Taylor expansion of the operator on the locus of the defect. Okay, so as opposite to this case, the other case is when the defect decouples from the bulk. And with this, I mean when the correlation function of the defect quantum field theory now factorize as correlation functions of the bulk times correlation function on the defect. And therefore, from the point of view of the bulk dynamics, there is no observable which can distinguish the situation in which we have or we don't have the defect. So in some sense, the defect in this situation is proportional to the identity. And the proportionality factor is just the value of its partition function. Okay, there is always a third scenario which is not present usually in quantum field theories without defects. And this scenario is the one in which this defect archiflow never ends. It never reach an IR fixed point. And this is usually called the runaway scenario. This is somewhat special, is a little bit exotic. And in this paper, these people claimed, at least they argued, that this scenario can only happen in theories when there is a modular space, for example, in free theories, but it's not very generic. So therefore, in the following, I will not consider this scenario. Of course, there is always this possibility, but I will try to avoid this possibility. And okay, what is the goal of our work? The goal of our work is to find generic conditions under which we can exclude one of these three scenarios. For example, conditions under which we can exclude at least the decoupling scenario. And if we find at least some way to constrain this archiflow, then we can say something non-perturbative without solving this very complicated archiflow. Okay, other question about this introduction and motivation. Otherwise, I will go to the study of the symmetries of this problem. Okay. Okay, so now let's talk about symmetries and defects and how they behave together. So let's consider for this purpose a bulk theory which has a symmetry G. So in this talk, for simplicity, I will consider at least now at the beginning a U1 zero form global symmetry, which is acting faithfully on the bulk local operators. And what does it mean when we have a Lagrangian to talk about? This means that we can find a transformation on the fields like this, such that the action is invariant. Okay, now we insert the defect in our problem. We modify the action, and then this defect quantum field theory may or may not break the global symmetry explicitly. And how we can detect this breaking? Well, if we have an action, we just have to find if there is some transformation on the edge modes, which leaves the defect action invariant. So what does it mean in terms of currents and correlation function? Okay, we know that in absence of the defect, if G is continuous, we get current J mu, which is conserved. So of course, if we add a local modification of the action, this conservation equation can be spoiled, but just locally. So if we apply another theorem, we will see that the divergence of the current now is not anymore zero, but it can be non-zero, but only locally on the defect. And the operator which control this lack of conservation equation is the so-called tilt operator. This T of x is very important. It is the so-called tilt operator. Okay, if the defect breaks the symmetry, then this tilt operator is non-trivial, and this means that the defect will carry some charge under the zero-form symmetry. This is the so-called generalized charge because it's not a charge that can be detected by a link configuration, just because the defect is higher dimensional with respect to the local operators. Okay, in this situation, there is a very interesting story about the role of the tilt operator. Indeed, one can prove that this tilt operator is protected as a protected dimension, and therefore it generates a conformal manifold in this set of operators, which is nicely described in this paper. However, today I want to describe the situation in which the defect does not break the global symmetry. And in this situation, one can show just by applying again another theorem, but on the defect action, that the tilt operator is now again a total derivative, and can be written as d mu of some new current little j. And then one can easily construct a new topological operator, which is topological even in the presence of the defect. This is just its form. Okay, so what does it mean in the language of topological operator that we all like? This means that the topological operator commutes with the defect, and also that it can intersect the defect, and in the intersection, this configuration is still topological.
There's a question, I think,
Yes.
Giovanni.
Okay.
Can you go back to the previous slide?
Yes.
Yeah, so I'm curious, so this T of x, you call it a generalized charge. Is there any quantization condition on this
No,
function T of x?
no, there is no quantization. I don't think T of x is the generalized charge. I mean
Oh,
that
sorry.
when T of x is not trivial,
I see.
then we can assign a generalized charge.
I see. Okay, sorry, I
By the way.
misunderstood.
So the physical intuition of this T of x is that if you fuse the topological operator on top of the defect, or if you wrap it, depending on the dimensionality, you get that the defect action is modified by this tilt operator. So this tilt operator gives you like the modification of the defect under the symmetry action, at least by infinitesimal transformations.
But suppose J generates the compact U1 global symmetry. Is there some global condition that T of x has to satisfy?
Okay. So I think yes, because this T of x you can think as like the marginal operator generating the U1 conformal manifold. So it must have some global condition on it, yes.
I see.
So the conformal manifold is compact, is U1.
I see. Okay, thank you.
Thank you. Okay. So this is the standard way of defining symmetric defects. But what we pointed out in our paper is that if we tune the dimensionality of the defect to be exactly d minus 1, then we can have a stronger condition on top of the symmetric defects. And the stronger condition is just the fact that the symmetry operator now can also end topologically on the defect, not just intersecting it topologically, but also end on it topologically. And what does it mean in terms of the current? This means that this happens when the current on the defect is a total derivative. you can check that this is a stronger condition with respect to this one. And in particular, this implies that we can construct this new topological operator, which is defined on a manifold which is open, and its boundary is topological only if it lies on the whole volume of the defect. Okay, so this is in terms of like pictures. As I said, that means that the topological operator can end topologically on the defect, but this also implies that the defect absorb the topological operator. So if we fuse them together, they have the same dimensionality in this case, the defect remains the same. Okay. This is just an advertisement of the fact that in the first version of our paper, we call these defects strongly symmetric, but then we realized that there was some confusion with a notion of a strongly symmetric boundary condition that that appeared in this paper some years ago, and therefore we decided to change the name in order to avoid confusions. And in the next version of the paper, we will call this defects symmetry reflecting. So, okay, what are the consequences of this stronger condition? No, sorry. First, I want to say something about the intuition of what does it mean. So, to have a better understanding of this stronger condition, we can use the folding trick. So, this is a well-defined procedure that we can do, for example, when we have conformal symmetry. So since the defect is codimension 1, we can fold this theory and get a new theory, the folded one, which is just the theory times its orientation reversal defined on a manifold with boundary. And the boundary is exactly the locus of the defect. So in this situation, it's clear that if the theory had a global symmetry G, then the folded theory will have a global symmetry G times G. And one can check that if the defect was symmetric, this implies that the boundary condition now will be symmetric just under the diagonal combination of the two G, the one that acts on the same way, well, with opposite charges on the degrees of freedom of T and the one of T bar. However, if the defect is symmetry reflecting, this implies that the boundary condition is symmetric under the full G times G symmetry of the folded theory. So in this sense, you understand that this condition is stronger and it implies the one of symmetric. Okay, so let me now describe the consequences of this new definition. So the first immediate consequence is that in this situation, the global charge is preserved independently on the left and on the right-hand side of the defect. And this one can be proven very easily. We can create our topological operator from the vacuum, assuming that the symmetry is not spontaneously broken. And then we can start moving this topological operator. And whenever it cross charged operator, we will get a phase. But now, when this operator will approach the locus of the defect, just from the definition of symmetry reflecting defect, we will get that the defect absorbs the topological operator. And therefore, we will not measure the charges of the operators which are on the right-hand side of the defect. So therefore, we will get these peculiar selection rules. For example, if we get a two-point function of an operator which in the absence of the defect has a total charge which is equal to 0 and therefore can be different, in principle different from 0, what we will get is that in the presence of the defect, this correlation function will be automatically 0 because the charge is not equal to 0 on the left and on the right-hand side of the defect. Okay, so we can think of this as like a symmetry which acts on all the degrees of freedom on the left, on half space. Okay, other question about these selection rules?
Is it
Okay,
possible
so
to drag
yes?
the charge OQ1 across the defect?
You want to do the OPE of OQ to the defect?
Yeah.
Yeah, so in a conformal theory, this can be done. but generically you can also have, let's say, singular terms. So this depends if the operator commutes or not with the defect. If it doesn't commute, it means that it has some say discontinuity on the defect. But of course, you can do an OP, and this will be like a linear combination of all the defect operators. Okay,
Thank you.
thank you. Okay, let me now do the.
Sorry,
Are
can
there
I
more
ask?
questions? Yes.
So, can you explain again why the notion of the symmetry reflecting only happens when the dimension of the symmetry defect and the symmetry operator and the defect are the same?
So in
For
the case
example,
of zero form symmetries, so we have that the topological operator is codimension 1. So we need
right.
to have that the defect, at least geometrically, the topological operator can end on the defect just from by dimensionality. And you can check that if the topological operator has dimension d minus 1, then the only possibility is that also the defect has dimension d minus 1. But in general, I will comment later that for a generic dimension of the topological defect, the condition is that the defect is bigger, has more dimensions with respect to the topological operator.
Oh, I see. Thank you.
Thank you. Okay, so let me now make the much stronger statement, which is the one about RG flow. So the statement is that symmetry reflecting defects cannot decouple along the RG flow. And okay, given the definition I gave to you, now I think it becomes clear why. And this is just the fact that the configuration of the symmetry operator ending on the defect is topological, as I was saying. And if you assume that the defect flows to the identity operator, now this contradicts the fact that the symmetry was acting faithfully on the bulk degrees of freedom. And this is just the statement that the identity defect is always symmetric, but is never symmetry reflecting, in the sense that a symmetry operator cannot end topologically on nothing if it acts faithfully on the bulk. Okay, so what we conclude is that symmetry reflecting defects, if we are able to find some symmetry reflecting defects, then we are sure that this defect will remain in the IR and will be non-decoupled. Namely, that we can do some bulk correlation function that will detect the presence of this defect.
May I ask a quick question? So
Yes.
I'm not sure I completely understood the argument, but just to be sure, here you're assuming that OQ does not decouple, right? Because it could be that
Yes,
all
yes.
charge operators decouple.
Yeah.
So
I'm assuming that in the bulk QFT, you can say or that the bulk QFT does not run, so the RG flow is localizing
I
on the
see.
defect,
Okay.
or you can also allow it running on the bulk, but you have to assume that the symmetry does not decouple.
Right.
Otherwise,
Thanks.
everything can decouple. Thank you. Yeah, this is a crucial assumption. Okay. So as I was saying, now we have two IR possibilities for these symmetry reflecting defects. And what are these two possibilities? The defect can flow to a non-trivial conformal defect, or it can flow to a faithfully acting topological operator. So namely some topological operator, but which still measure the charges of this OQ in order to make this configuration consistent. Of course, we are assuming no runaway, otherwise the runaway scenario is always compatible. Okay, so let me make some final comments on these symmetry reflecting defects. So the first comment is that a defect can never be symmetry reflecting under an anomalous symmetry. And this is very similar to the statement that boundary conditions cannot be symmetric under anomalous symmetries. Just the fact that the symmetry cannot end on something if it is anomalous. The second comment is something that I was already saying before to Yunkin, is that we can generalize this notion to Q-form symmetries, but now we can allow for more dimensionality of the defect. In particular, any p-dimensional defect can be reflecting under a Q-form symmetry if P is greater or equal than the dimension of the topological operator, which is D minus Q minus 1. And the other comment is about non-invertible symmetries. And here it comes the relation with this paper that I was mentioning before. Indeed, we can also allow for the notion of symmetry reflecting defects with non-invertible symmetries, but in this case, we have a further classification. And this is just because if we have a symmetry which is non-invertible and ends on something, this does not mean anymore that the symmetry is absorbed by the defect. These are two different notions in this case, and then we have two different classifications. Okay, other question about these symmetry reflecting defects? Otherwise, I will move to another constraints on the energy flow.
For the higher form symmetry case,
Yeah.
and is invertible, when P is not codimension 1, then you can no longer do the folding, right? To
Yes,
relate
yes.
to the folded theory. So previously, you have this nice distinction between, the symmetry in the folded theory, the defect in the folded theory, the boundary in the folded theory is either G symmetric or G cross G symmetric.
Exactly.
Now, but in the case when P is not codimension 1, is there a similar way to characterize
Yeah, I don't
it?
know.
Uh-huh.
Yeah, I don't think there is this nice interpretation as the defect as a double symmetry like G times G, because now there is no
Right.
Z2,
Right.
but there is a
Right.
U1 rotation along the defect. Maybe this
Right.
can be useful,
But
but I don't have.
right. So previously you distinguish ordinary symmetric defect versus a defect that satisfies symmetry reflecting condition. And the difference is that either you have one copy of the G selection rule or two copies of the G
Yes.
selection. Now, in the case when P is not codimension 1, do you still, in a sense, have like more selection rules compared to the?
Yeah, I think we don't have more selection rules because, as you say, that there is no
Right.
all space to use, but
Right.
still you have this statement, this one, because this just comes from the fact.
Right. This
Yeah.
I understand, but
Yeah,
but
yeah.
do you still have two
So
notions of a defect being symmetric?
the difference between the two, you mean?
Yeah, I
Yeah,
thought
yeah.
earlier you have two notions of a
Yes.
defect being symmetric.
Yes.
Is there still such a distinction?
Yeah. I think there is this distinction because even for uniform symmetries, you can distinguish between the fact that the defect can end topologically or can just intersect it topologically.
Right.
So if you think about currents, so if you think about continuous uniform symmetries, this is very clear because this distinction between J being a total derivative or not, this is something sharp. For discrete symmetries, we have to make this distinction
I see.
about ending or not.
I see. Okay.
Yes, but I agree that the selection rules are valid only for interfaces. Thank you for the
Okay. Thank
for the
you.
comment.
Thank you.
Thank you. Are there more questions about? Okay. So if not, let me now comment about anomalies. But before doing that, let me now introduce the notion of background gauge fields. So now that we defined what we mean by a defect to be symmetric, either symmetric or symmetry reflecting, we can now discuss what does it mean to couple the defect quantum field theory to background gauge fields. So let me now discuss the case in which the defect is just symmetric, the standard notion of symmetry. Then we have this current big J of the bulk and the current little j on the defect. And therefore, we can couple in a minimal way the backgrounds to this theory just by doing A wedge star J on the bulk and on the defect. So if you now impose that this theory is background gauge invariant, just by using the conservation equations for the two currents, we will understand that this implies that this curly A must be the pullback of the big A. So at the end, we will have just one background gauge field, which will be this big A and its pullback value on the defect. And what does it mean in terms of a topological operator? So we know that at least when we turn on a flat background, this is equivalent to inserting a mesh of topological operators on the spacetime. And since the defect can be crossed topologically by these symmetry operators. This implies that we can produce the same mesh as in the theory without the defect, because the defect is more or less transparent with respect to the symmetry. The symmetry does not feel the defect, and therefore we can put the same mesh as before. And this is the statement that we have the same amount of backgrounds with respect to the ones that we can cook up in the theory without the defect. So what happens now when the defect is symmetry reflecting? So I'm considering the case of codimension 1 symmetry reflecting defects. So the one that divide the space-time into two half spaces. So in this case, we realize that we can turn on backgrounds which are more general with respect to the one present in the theory without the defect. Indeed, we can turn on a background A left, a background A right, and then this curly A is just the pullback of the difference. So there is no relation between A left and A right. And this is very clear from the point of view of topological operator. It's just the fact that in the presence of the defect, we will have more topological configuration with respect to the ones present in the theory without the defect. It's just the fact that the symmetry operator can end topologically, and it is a configuration that is not present in the theory without the defect. So in this sense, there is again this intuition that for strongly symmetric, for symmetry reflecting defects, which are codimension 1, there is this symmetry which is doubled on the defect, is G times G instead of G. Okay, so now that we have this notion of background gauge fields, we can define a defect anomaly in the standard way, just by saying that the partition function is not quite gauge invariant under background gauge transformation. And the lack of gauge invariance is detected by this phase, which is the anomaly phase. And just by the locality of the defect, we will find that this phase gets two contributions. One, which is integrated along the full space-time, and it is the standard anomaly of the bulk theory. But then we will get a new contribution, which is localized on the locus of the defect. And this is what we will call the anomaly, the defect anomaly. So at least this will be a defect anomaly if this phase cannot be cancelled by redefining the coupling of the theory to the backgrounds, so by adding some counter terms. So what I want to stress is that the defect anomaly can be present even if this bulk anomaly alpha D is equal to 0. For this will be a defect anomaly without a bulk anomaly, is an intrinsic notion of the anomaly of the defect. Okay, so as you can imagine, the defect anomaly must be patched along the energy flow. And there is, again, this very nice picture of anomaly flow, which makes the defect quantum field theory background gauge invariant, just by adding an extra dimension. But now, on top of the standard anomaly flow, which cancel the phase which comes from this space-time contribution, we will get another anomaly flow, which is now defined on p plus 1 dimensions, and which will cancel the lack of gauge invariance that is gets contribution from the defect. So okay, you can think now the defect has to be at the boundary of an SPT, which will cancel the defect anomaly. So, however, what I want to argue is that this defect anomaly does not imply that the defect cannot decouple. And this is just because the dynamics of the defect itself can match the anomaly without the need of introducing a coupling to the bulk. So therefore, it is still compatible, that is still a perfect good situation to have an energy flow with a defect anomaly in which the defect decouples and cannot be detected by the bulk operators. The only constraint that we will get from a defect anomaly is that the defect hyperspace cannot be one-dimensional, as usual when we have anomalies. So let me give now some examples. The first one is let's say a trivial example in the sense that is a little bit ad hoc, but it's just to show that the defect anomaly can be matched by a decoupling scenario. So let me construct a defect just by considering a d-dimensional theory T with a U1 symmetry. And then we consider a p-dimensional theory T tilde with, again, a U1 symmetry, and we construct this defect quantum field theory just by summing the two actions and then introducing a coupling of the theory T tilde to the theory T. So O will be a bulk operator of charge Q under the U1, and phi will be a defect operator, in the sense that an operator of the theory T tilde, which has a charge minus Q under its U1 symmetry. So it's clear that this defect action will be symmetric under the diagonal combination of the two U1 symmetries, and therefore the defect will be symmetric under the U1 symmetry of the bulk. Okay, if we now choose T tilde to be a theory which has its own anomaly, Toft anomaly for its U1 symmetry, then it's clear that from the definition I gave to you that the defect quantum field theory will have a defect anomaly for the U1. However, since the defect anomaly is produced by this action and not from the coupling to the bulk, is evident that this theory is consistent with the procedure of sending the coupling to the bulk to 0, just because the anomaly is matched from the dynamics of the theory T tilde itself. Okay, let me now present some more non-trivial examples. The first one is about line operators, and this is something that is very is well known in the literature. For example, you can look at these very nice papers. And this is the statement that line operators, which transforms projectively under some global symmetry of the bulk, have some sort of anomaly. And this fits very nicely with our definition of defect anomalies. So for example, let's consider quantum electrodynamics with NF scalars. So we know that the global symmetry of the bulk theory is PSUNF instead of SUNF, just because the center of SUNF is part of the gauge group of the theory. And therefore, we can turn on background gauge fields for this PSUN global symmetry, such that Stephen Wittig class is different from 0, or at least it's integral. And this implies that the Chern class of the U1 gauge field is now fractionalized with a fractional part which is fixed by the Stephen Wittig class of the background gauge fields. And this implies that the Wilson line of the theory now are not anymore background gauge invariant, just because in the presence of B, the field strength is not anymore quantized, and this implies that the holonomy is not anymore gauge invariant. And in order to make a line which is gauge invariant under the background gauge transformation of P, then we have to consider a line which is the boundary of a disk in which we integrate this Stephen Wittig class. Okay, let me just mention that this is very generic. It happens anytime we have some lines which transform projectively under the bulk global symmetry. For example, it can happen in SUN gauge theories with fundamental quarks if we have, for example, some U1 baryonic symmetry. Okay, let me now present a final example, which is about the symmetry reflecting lines. And with this intuition that the symmetry is now doubled on the defect. For example, if we consider a line in 2 dimensions and we consider it to be symmetry reflecting under a Z2 global symmetry of the bulk, then we know that these Z2 lines can end topologically on D, and then we can consider the situation in which these endpoints cross, and when they cross, generically we will get a phase which is classified by this cohomology group, at least if we don't include fermionic symmetries. So you see that the symmetry is Z2, but the anomaly is classified by Z2 times Z2. And this is again the fact that the symmetry is doubled on the defect. Okay, are there questions about this notion of defect anomalies? Okay. So what is the claim?
For the Wilson
Yes?
line in the previous example, what can
Yeah.
match the anomaly in the IR?
You can match the anomaly by a decoupled TQFT in 1+0 in a quantum
I
mechanics.
see. So just free queued it. I
Yes.
see. That makes sense.
So the only statement that you can make is that the Wilson line cannot flow to the identity, but can flow to some number proportional to the identity.
Right.
Just
Right.
Okay, thank you.
Thanks.
Okay, so what is now the claim? The claim is that combining all these RG invariant quantities, which is this similarly reflecting defect, these defect anomalies, and also using the monotonicity theorems I defined in the beginning, one can sometimes even solve the RG flow exactly. So let me present an example of 2D CFTs with line defect. Okay. So a huge class of defects which are constructed in the literature are obtained by deforming the identity with some relevant operator. For example, we can take an operator O, and if this operator is relevant in one dimensions, namely the conformal dimension is less than 1, then we can integrate it on the line, and this will trigger an energy flow, which will define for us a line defect in the theory. So what we want to do is to slightly generalize this picture in order to construct a non-trivial symmetry reflecting defect.
But before you generalize this,
Yeah.
for
Yes.
this kind of line defects, suppose O is symmetric under the global symmetry.
Yes.
This defect, I assume, will be symmetric, right?
Exactly.
But it's not going to be symmetry reflecting generally.
No.
And can such a defect be carrying anomaly? I guess no.
I guess no. No, you cannot.
Because you can take lambda to be 0,
Yes.
then it becomes a trivial defect, which doesn't have any anomaly.
In the UV is the identity, so it's always
That's right.
not anomalous.
That's right. It's connected to the identity.
Yes.
Right? Okay, thanks.
Thank you. Okay, so for concreteness, let me take 2D icing, which has a Z2 symmetry, but this can be easily generalized, and we did in the paper. So we have a topological defect line, which is eta, which is square to the identity. And of course, in this theory, there is always a topological defect, which is symmetry reflecting. And this is just the combination 1 plus eta. So we know that 1 plus eta has absorbed the Z2 symmetry, and also the eta line can end on this non-simple topological line. And now what we want to do is to take this UV symmetry reflecting line and turn on a deformation on top of it. And as we were saying before, if this deformation is Z2 symmetric, then we will know that d lambda will be symmetry reflecting. Okay, so now the problem is to understand what are the possible deformations which one can turn on top of this topological line. And the possible deformation are the one corresponding to states which lives in the Hilbert space twisted by the product of D with its orientation reversal. So there are two kinds of deformation. Since D times D dagger is again 1 plus eta up to normalizations, then we have two different deformation. One is local deformations. What I mean with local, I mean operators which are genuine local operators of the bulk theory. But these deformations are not very interesting for us, just because since these are deformations that can be turned on the bulk, this implies that this d lambda I'm defining here is just factorized. Since DUV is topological, we can define DUV not on the same locus of this local deformation. We do the RG flow on just of this operator, which is the one described here. And then we fuse the two results in the IR. So I think from this perspective, this is not something that one can, let's say, constrain this scenario just by using the symmetries. So the more interesting situation is when the deformation we are turning on the defect is a twisted deformation, namely a deformation living on the Hilbert space twisted by eta. And of course, this is an operator which is non-local in the bulk, and therefore we cannot turn on this deformation on top of the identity. But since D absorb eta, this becomes a local deformation on top of DUV. Therefore, is a well-defined procedure to integrate this non-local operator on top of the symmetry reflecting topological line. So now the condition is just to find an operator living in the twisted Hilbert space of eta, which is Z2 symmetric. And if this operator exists, then we can construct, and of course it must be relevant. So with dimension less than 1. Then we will find a non-trivial defect RG flow, which we know must be not decoupled in the IR because of the symmetry reflecting nature of the line. And in Ising, there is a very simple operator which fits all these requirements, which is the disorder operator mu. You can check that mu is relevant, is Z2 symmetric, and it lives in the eta twist sector. Okay, so the defect that I will considering is this one. And what are the things that must be matched along the RG flow? So as I was saying, is Z2 symmetry reflecting, therefore it cannot decouple in the IR, and in the IR must be some line some line defect which is symmetry reflecting, either conformal or topological. The second requirement is that in the UV, the G function of this defect is 2, because the G function for topological lines is just the quantum dimension, and for 1 plus eta, the quantum dimension is 2. Therefore, in the IR, this G function must be less than 2. And the third thing that must be matched is the defect anomaly I was mentioning in the third example before. So in this case, in the UV, if we do this movement, the 1 plus eta will get a plus sign. So in this sense, as a trivial defect anomaly. So in the infrared, it must have, again, a trivial defect anomaly. So, but now in the Ising CFT, we know all the possible topological lines. These are 1, eta, and n, where n is the Kramers-Vanier duality defect, and all the possible linear combination of them with integer coefficients. Now we have to look at the possible symmetry reflecting lines in this set. And the only ones are n, 1 plus eta, and all the possible linear combination. But the only one which has a G less than 2 is n, because already 1 plus eta is dimension 2, and all the possible linear combination will have G greater than 2. Therefore, the only candidate for a topological line in the infrared is n. However, in the Ising CFT, n has a non-trivial defect, Z2 defect anomaly, which is encoded in the F symbols of the categorical symmetry of Ising. Therefore, this cannot be the IR fixed point of our defect. And this implies that putting together all this information, we conclude that the IR of this defect must be a conformal line. Okay, in the Ising CFT, we also know all the possible conformal lines of the theory. And we can solve the RG flow. And what we find is that the defect in the infrared becomes a factorized defect, namely a product of two boundary conditions. And the boundary condition that we get is the one which is Z2 singlet, such that this defect in the infrared is symmetry reflecting. And it has a trivial anomaly just because it's factorized. So the end line on the left cannot fill the endpoints on the right. Okay, are there questions about this example? Okay, so if not, we'll just mention that we have some other examples in the paper. For example, one can do a similar construction for all the minimal models in the diagonal modular invariant theory. We know that these minimal models, they all have a Z2 symmetry. And just by a simple analysis of the twisted Hilbert spaces of these theories, we can see that there is always a relevant Z2 singlet and twist and deformation, which can be turned on top of 1 plus eta. Also, we can do a similar game in the C equal to 1 compact boson. and in this case, we can also turn on a relevant deformation on top of simple lines which are symmetry reflecting, which are the duality defects of the theory. And we also have an interesting case, which is the case of a symmetry reflecting surface in 3D abelian gauge theories. And these will be surfaces which are symmetry reflecting under the U1 topological symmetry of the bulk theory. Okay, so let me conclude. So I've shown that extended defects in quantum field theory can enjoy very interesting behaviors when there are symmetries present in the bulk and the dimensionality are tuned to some fixed values. And we introduced the notion of symmetry reflecting defects and defect anomalies. And of course, there are a lot of questions that I can make. These are two that I'm interested about, which is if one can find some universal construction of symmetry reflecting defects in higher dimensions, and also if there are more constrained consequences that one can make from defect anomalies if we look for some particular kind of anomalies. So with this, I end and thank you for your attention.
Well, thanks very much. It was a nice talk. Are there more
Thank you.
questions? I mean, you had already loads of questions, but maybe there are some more. Yeah, Giovanni.
Yeah, thanks for the very nice talk. I really
Thank you.
enjoyed it. So for your outlook number one, I guess one obvious way to construct such symmetry reflecting defect is to use factorized defects, right?
Correct,
Okay,
yes.
so that's one obvious class, I think. My second question is perhaps it's not really about physics, but maybe it's just about maybe it's more philosophy. So you distinguish the notion of symmetry reflecting defects versus defect anomalies.
Mm-hmm.
But both of them have non-trivial consequences on the low energy limit of the defect. In fact, in a sense, the symmetry reflecting property is even stronger than the defect anomaly, right? It tells you that it
right.
cannot even decouple. So maybe my philosophical question is, should I think about the symmetry reflecting property as some kind of more generalized defect anomaly?
I think the let's say one problem can be that I don't know how to classify. There is no classification of this as symmetry reflecting property, while for anomalies, at least in our examples, is always classified by some cohomology group. But I don't know if there is some, let's say, discrete quantities that makes the defect symmetry reflecting. Yeah, I didn't think about it. But yeah, I don't know. But I agree that
Okay, go ahead.
I agree that symmetry reflecting is a property that is stronger with respect to defect anomaly, even if it seems like usually is the opposite in quantum field theory, that anomalies are stronger with respect to just symmetries.
Right. Okay. Thank you.
Thank you.
There was another question in the chat, but I think maybe that has been resolved or not. Actually, I don't think it has. If you just take a look by e-rating.
Rajat, have a question?
I just want.
Yeah, let's go first with the question in the chat. Yi, if you
Okay,
want to comment on this.
Yeah, I just want to ask for the higher form symmetry, if we want to couple the symmetry to the background gauge field, is there a similar way to do that, like what you did for the zero form symmetry?
So if the higher form symmetry is continuous, is the same. Just the fact that if it is symmetry reflecting, you don't have anymore this distinction of left and right. Otherwise, if it is discrete, we don't have the notion of, let's say, local gauge connection. Everything is flat. And therefore, we can rewrite the coupling to backgrounds as a mesh of topological operator. Therefore, we have this notion of background as like writing some lines in the theory with the presence of the defect. So I think, yes, we can do the same analysis for higher form symmetries.
Then what is the difference between symmetry reflecting defects versus just symmetric defects?
Yeah, so I have this intuition that you have still more possibilities because you can write line, let's say, operators which end on the defect, but it's not anymore, let's say, you don't have anymore this clear interpretation as the space of backgrounds are the one of G times G. It's not anymore true, this. So I don't have a clear answer to this question, but intuitively you still have more backgrounds to turn on.
I see. Thank you.
Raja?
Yep. Yeah, thanks for the talk. I have a basic confusion regarding this symmetry reflecting defect cannot become trivial because you have this non-trivially acting topological operator, and that you don't want it to end on the identity defect, right?
Yes.
But if you have something like condensation defects, they can act non-trivially on other operators even though they admit gap boundaries, right? So how should
Yes.
I understand this scenario?
Yeah. When I say acting faithfully, I mean that it acts faithfully on local operators or by operators which link with it. Otherwise, I agree that operators which do not act on anything by linking can be cut open and topologically. But in this case, if some defect is symmetry reflecting under a condensation defect, I don't know if it is possible, but if it is possible, then you cannot conclude anything. I agree.
I see. Okay. Thank you.
I don't see any more questions. I'd like to thank Giovanni again for his nice talk, and I'll
Thank you.
stop the recording.